but just like before, because the audio is like tied to the projector, so I cannot control like the audio from here. And if Janet, you have a question, you can raise it in the Zoom chat. Okay? Right. So let's pick up from where we were last time. Okay. So we saw at like the transition metal. Okay, like reaction, and we said okay there are many different oxidation states for transition metal, and this allows them to act as oxidizing or reducing agent. Right. Okay. So today we will look at a special case where transition metal acts as a catalyst. Okay. Right. So you may want to put this on your note. We are not using the worksheet just yet. We'll finish this discussion first. So transition metals and catalyst.
Too much.
Right. Okay. So because some reactions, they are kind of slow by themselves. Let's put down this example. I minus and S2OA2 minus. The two would react to give I2 and 2 sulfate ions, you see. So we have 2 iodide reacting with 1, S2OA2 minus to form 1 iodine and 2 sulfate. Okay. This reaction, they will ask you why is it very slow by itself. Can you all think of reason why this reaction without a catalyst is very, very slow by itself?
Iodine is solid.
No, but you may want to look at the charge of the reactant. What does the charge of the reactant tell you about their interactions? Do they attract each other or do they repel?
Repel.
They repel, okay? So the first question that you will have to know the answer to is, why is this reaction, extremely slow without a catalyst added? Okay, so extremely slow without a catalyst added. So the answer actually lies in the charge of the reactant, you see. So the answer is because both reactants are negatively charged. And so you should know some simple physics. If there are two like charged things, they don't attract, they repel. Okay? So both reactants are negatively charged, so they repel. It's unlikely for them to collide with one another effectively. Okay, so they repel. Therefore, this reduces collision. Yeah, so reduces the frequency of collision. Right. Yeah. Okay. Yeah. So it reduces the frequency of collision, and therefore reduces the rate. So this reaction, you can assume, without a catalyst, is extremely slow. Okay, slow to a point that you may think that it didn't occur. Okay, but then we can change this by the addition of a catalyst. Okay, Fe3 plus or Fe2 plus catalyst. So yeah, copy this equation first. Very important, and it's already been balanced for you. Okay, just focus on the charge. So how can we make this reaction go faster? So we can speed up this reaction by adding a catalyst. Okay, so by adding Fe3 plus catalyst. Actually, an Fe2 plus catalyst will also work, and I'll show you that as well later. But first, let's just use Fe3 plus as a catalyst. So the Fe3 plus ion, it can exist in two oxidation states. Okay, so we call that iron is a transition metal, which means it can exist in multiple oxidation states. Okay, so therefore it can have +2 and +3 oxidation states. Okay, when Fe3 plus turns into Fe2 plus, can you tell me what kind of reaction is this when Fe3 plus becomes? This is reduction, yes, so put down reduction here. Similarly, when Fe2 plus goes back to Fe3 plus, we will call this oxidation. So because iron can go between these two oxidation states, okay, we say it can't catalyze this reaction. Let's see how. So the iron 3 plus, okay, I think you can draw a diagram that looks like this now. Okay, so where you have I minus and S2O82 minus. So you see at first the I minus and S2O82 minus, they have no reaction between them, or you can say there's very, very slow reaction between them because they repel. Okay, so repulsion occurs when there's no catalyst added. However, as soon as you add the Fe3 plus catalyst in, the Fe3 plus will turn the I minus into like a I2. Okay, in this process, the Fe3 plus is reduced to Fe2 plus. Okay, I'll write you an equation, don't worry, but copy this first. The iron 2 plus, after reacting with I minus, it will turn it into Fe2 plus. And you still see the S2O82 minus left behind, okay, on the side. Okay, you see the S2O82 minus did not get reacted at this point yet. And by the way, this is a time lapse, like a process here, okay, showing you what happens at the beginning without any catalyst. Without any catalyst, you see they hardly react. So how can we change that? We add the iron 3 plus catalyst. Once you add the iron 3 plus catalyst in, the iron 3 plus and the I minus, they can react. So can you tell me why won't these react when these two can react? Because look at the charges now. Are they like charged or oppositely charged? Oppositely charged. So that means while here there wouldn't be any reaction, or it would just be a very slow reaction because they repel. Here, iron 3 plus has a much higher tendency to react with I minus. Yes? The soon. But then just now she was in the Zoom chat. Okay, yeah, maybe you can ask Janet to try again. Okay, yeah. Anyway, there will be a video to refer to, but I still want her to join if she can. Okay, yeah. So put this down first. The Fe2 plus. Okay, so she's back. Right. Right. Hello, Janet. Okay, can you see the screen? Okay, if you can see the screen, or if you cannot see the screen, like type something out in the chat box. Yes. Okay. Yeah. So, and feel free to raise question in the chat box, Janet. Okay. So, okay, I'll refer back to this charge from time to time. So the Fe2 plus is now formed. Okay, Fe2 plus will then react with S2O82 minus and turn it into SO42 minus. Okay, in this process, the Fe2 plus is converted back to Fe3 plus. Okay, so we can summarize these reactions with the following equation. Yeah, I know it looks like a mess. Okay, so let me break this down now. You have Fe3 plus reacting with 2I minus. This converts the Fe3 plus into Fe2 plus. At the same time, the I minus is converted to I2. Okay? And then the 2 Fe2 plus will react further with S2O82 minus to form back the 2 Fe3 plus. And you get the other product. What do you notice when you add up these two equations? Okay? So you can draw a box over here first. This you can call it the uncatalyzed reaction. There's no catalyst added, so uncatalyzed reaction. Below, this is what we call the catalyzed reaction. There is a catalyst added. So the catalyst being Fe3 plus. So catalyzed reaction. Tell me what you notice when you add up these two equations. When you add these two equations, which term or terms will be eliminated?
Fe3 plus and Fe2 plus.
Yes, Fe3 plus and Fe2 plus. And you know what? When you add them up, you get back the same equation as you did before. 2I minus plus S2O82 minus forming I2 and 2SO42 minus. What does it suggest? It suggests that the catalyst is really not consumed or produced. Okay, because when you take a look at this here, don't mix up Fe3 plus and Fe2 plus. I know the charges are very similar, but they are clearly different things. What do you call something that is used in an early step and reformed in a later step? You call it a catalyst. What about the substance that is formed in the first step and then used in a later step? There's an I word for this, which we learn in organic chem. What do you call the things between the reactant and products that get formed in the middle? Intermediate. Yeah, so can you draw these symbols on the side? Intermediate. So they have different roles. Don't mix them up. Okay, so this rhombus here and this rectangle, they represent different things. The rhombus represents intermediate. Intermediate. So the rectangle, Fe3 plus, okay, the rectangular term represents catalyst. So what's the difference between an intermediate and a catalyst? An intermediate will be formed in an earlier step, but then it will be reused in a later step. Okay, but reused in later step. What about catalyst? It's just the reverse. It is formed in it is used in an earlier step, but then it is reformed in a later step. Okay, but overall, they will both not appear in the overall equation. Okay, so they are used in an early step, but reformed in later step. Do you see the difference? Okay, this is the difference between a catalyst and an intermediate. But there are some similarities, okay, between these two. And this is that they both, do they not appear or not appear in the overall equation? They will both do not appear in the overall equation. Okay? Because they will get crossed out, you see, on the two sides. Okay? So write down these are the differences. So these are the differences between intermediate and catalyst. What about the similarity? The similarity is that both the intermediate and the catalyst, okay, will not appear in the overall equation. So will not appear in the overall equation. Right. So now we can also look at this reaction in a different way. Okay, so yeah, copy this first, and also the equation. So you will need to know how to balance these two equations. Okay, and that can be done very easily. How? So you can first draw this.
Sir, can you zoom in?
Yes. So you have intermediate and catalyst difference. So Fe2 plus is the intermediate,
One what?
and Fe3 plus is the catalyst.
Right.
Okay, so you should also copy this catalyzed reaction on the left.
The
So
last two.
why can't a main group metal act as a catalyst? Okay, you may be thinking. That's because so form in earlier step but
The green
reuse.
one. The green one.
The green one. Both the intermediate and catalyst will not appear in the overall equation. So both the intermediate and the catalyst will not appear in the overall equation. So this being the overall equation.
But the intermediate also speeds up the reaction.
No, intermediate is just something formed in the middle of the reaction. But if you are asking, can Fe2 plus be the catalyst? Actually, Fe2 plus can also be the catalyst. If you make this your first step, if you swap the order of these two reactions, if you make this your first step, this will be the catalyst instead. In other words, adding iron 3 plus or iron 2 plus will speed up the reaction. Okay, because you may as well write this equation in the opposite order. You can write this equation first, and in that case, the Fe2 plus will be the catalyst, right? Yeah. So, and I like this other take on this reaction on the textbook, okay, which you'll find. So you have I minus becoming I2. So when I minus becomes I2, is this oxidation or reduction?
Oxidation.
Oxidation, okay. In this process, okay, you know redox. Redox means when this is oxidation, something must undergo reduction. Okay, so and that is the iron 3 plus and iron 2 plus. Okay, so iron 3 plus will have to undergo reduction. Okay, yeah, I think I should put the arrow here so you can see duration. This is ox and this is red. So we call this redox. So redox means every time you have a redox reaction, something must be oxidized, something must be reduced. This is what happens in step 1. Yeah, maybe you can put down step 1 in here, so we can refer to this more easily. So what happened in step 1? This is what happens in step 1. Step 1 is a redox reaction. Okay, so let me write down Fe3 plus. You don't have to copy this again. We already wrote that down. So I'm just putting it here so you can see it more clearly. In this process, iron 3 plus is reduced and I minus is oxidized. This equation shows the exact same thing you saw in the top diagram. But then, iron 3 plus, after becoming iron 2 plus, it will not stop here. It will then undergo another round of redox reaction. This time, it will start working on the other reactant. Okay, so in this case, it's S2O8 2 minus. It will become SO4 2 minus. Yes?
Do we learn back to redox?
Do we? You mean will we talk about
we
redox?
learn a new thing or like we just revise for the.
Oh, this is just a recap on the redox. This is not something new.
Oh.
Okay, this is not something new. Okay, so you can put down another redox reaction here. So here's another redox, and this is step 2. So you can write down, just copy step 2 you had earlier, and tell me again what is oxidized and reduced. So when you look at step 2, yeah, what is oxidized? In step 2, let me copy the equation first. 2Fe2 plus plus S2O8 2 minus becomes 2Fe3 plus and 2SO4 2 minus. Can you work out the oxidation number of S in this equation? Yeah, so I'll tell you the other.
7.
Yeah, for the top one, this will be plus 7. Yeah, don't forget the sign. Okay, yeah, so all of you got the number part right already. Okay, don't forget the sign. What about the S in SO4 2 minus?
6.
Plus 6. Okay, so write down plus 2 plus 3 and 0 negative 1. When you consider the oxidation number, don't look at the mole ratio. Mole ratio has nothing to do with the oxidation number. So even though you see 2 Fe2 plus here, the oxidation number of Fe2 plus is still plus 2. Yeah, mole ratio tells you only how they react. In what ratio they react. They don't affect the oxidation number. So here's a recap. When oxidation number decreases, we call this reduction. And when oxidation number increases, we call this oxidation. Okay, so we have oxidation here. So oxidation. Right, so I think this diagram kind of summarizes what is happening here. And yeah, so let me just put down reduction, and this is oxidation. So this is oxidation. So this is what happens in step 1 and step 2 respectively. Step 1, step 2. Okay, so this will be step 2 in here, and this will be step 1. Right, I think remembering this chart is easier than remembering these equations down at the bottom. Okay, so yeah, maybe split it into half when you remember. Do you know what is happening? Do you know what is happening? Yes. Okay. So now to wrap this up, okay, we have to understand a few reactions that involve the transition metal catalyst. They are very, very important. So just one more thing. So on the next page, put down some examples of transition metal. So transition metal as catalyst. Yeah, so you should know that transition metal, not only are the atoms catalysts, the compounds can sometimes also be catalysts. Sometimes it is the oxide that is a catalyst. Sometimes it is the ion, sometimes it is the metal that is a catalyst. So write down, transition metal can be catalyst in the following states. Okay, in number 1, elemental states. For example, iron. So iron is an element, you see. It is the catalyst used in the Haber process. So you must know the name of this process. We learned this in the equilibrium chapter, remember? So Haber process is named after the German scientist, okay, Fritz Haber, who worked for Hitler, okay? So he made ammonia, which can then be used to make two things. One is fertilizer, the other is explosive, okay? So that's why we say he may have killed million people, but at the same time he saved billion people. Because fertilizer can make crops grow better, but at the same time he also makes an explosive. Okay, so you can say, I don't know, maybe you will be judged, I don't know. So here you have 1, 3, and 2. And can you put down the catalyst in the iron? So iron is an element in the elemental state. What other states of transition metal can be catalytic? So in the oxide state, okay, an example, yes?
For the Haber process, do we need to write out the 200 API and 400?
Yeah, you need to remember the conditions, okay? So it's 200 ppm and about 450 degrees Celsius, okay? Yeah, so these are what we call conditions. The term conditions include catalyst use, temperature use, pressure use, okay? So write down conditions. So when you see the word condition, when they ask you to state the conditions, it means one of three things. Number one, it means the catalyst, yeah, if any. Some reactions do not have catalyst. In that case, just don't write the catalyst. The second thing will be the temperature requirement. The third thing will be the pressure requirement. So in no particular order, you can put them in any order you like, okay? So just have all three included in your answer. They can also be catalytic in oxide states, okay? For example, this one. This is called vanadium 5 oxide. So remember, whenever we write a Roman number, that represents the oxidation number. That is not the charge, okay? You cannot have something forming a 5 plus charge. Because forming a 5 plus charge ion means losing 5 electrons. That's a lot of work for an atom. So this is not charge, it's just the oxidation number, or V, okay? So you can put down, this is the oxidation number of vanadium in vanadium 5 oxide. So just set up an equation if you don't know how this is found. Okay, so you have X times 2. What is the oxidation number of each oxygen?
-2.
-2. So and you see they add up to 0 because this thing is a compound, meaning it's uncharged. So if you see a charge here, you then put the charge here, but you don't see any, so you put 0 here. So X will be +5. Okay, don't forget the sign plus. Okay, in your answer. So what does vanadium 5 oxide catalyze? I almost forgot. Write down the name of this reaction. Haber process. The making of ammonia, we call this Haber process. We have another process known as the contact process. Okay, so contact process involves sulfur trioxide, which is an important molecule for making sulfuric acid. So when you combine sulfur dioxide with oxygen, you get sulfur trioxide. So the reaction here is catalyzed by V2O5. Okay, so I'm just worried that they will give you another equation here and have you figure out what is the catalyst, what is the intermediate. So I'm writing it down. But this equation you don't have to memorize it. But I want you to use this as a practice. Okay, copy it still, just don't memorize it. Okay, we have SO2 plus V2O5 becomes VO2, and then you have VO2 plus O2 becomes V2O5. Okay, and let me put down SO3 in here. So I want you to identify the catalyst and the intermediate in this reaction. Okay, let me finish balancing this here. You have 2, and then you have V2 VO2 and 1/2 O2 giving V2O5. So can you identify the catalyst and the intermediate in this reaction? Which is the catalyst?
V2O5.
V2O5. Okay, so you may want to draw what was that shape I used earlier? What was it? A rectangle? Yeah, rectangle. Okay, for catalyst. Let me keep things consistent here. So this is the catalyst. Why? Because it was used in the first step. You see, it was a reactant in the first step, meaning it was used. But then it was reformed, regenerated in the second step. This is the catalyst. And what makes VO2, what is VO2 then? It has to be an intermediate. Yeah, so you see, I can give you any number of examples, and yet the same rule applies. If you see something being used in the first step, but then regenerated later, those are catalysts. If you see something formed in an earlier step, but then reused again, okay? That means overall none of them appear in the overall equation because they appear and go. They come and go, they come and go, okay? So therefore they don't appear in the overall equation. So you will find that when you add up these two equations, you get back the same one as this one. Yes?
About writing equation, the only fraction can be write in the end of equation.
The what?
The mole ratio.
The mole ratio you can write in any number. Yeah, but in here, I know what you may be thinking right now. When you add up the two equations, do you notice that this is not exactly the same equation as the one on top, right?
Yes.
Yes.
Times 2.
Yeah, this one will multiply by 2. I mean, if you like, you can multiply everything in here by 2 again. But I keep it this way because I don't want to make the mole ratio too large. Yeah, you can totally multiply both of these equations by 2. And then I can guarantee you that you will get the same equation on top. So this is what I meant. So let me copy this real quick here. I'm going to make this 2, 2, 4, 2. And then this will be 4, 1, and 2. Then now you will get the same equation as on top. Do you get it? Yes?
Yes.
Yes. So you have 2 SO2 plus O2 giving 2 SO3. So this is vanadium hydroxide. They can also catalyze like a reaction in the ionic state. So here, ionic state. For example, like the one we saw, Fe3 plus. Okay, so just know the name of this reaction. This is contact process. Yeah, the condition you might also want to know is 2 atm or 1 atm and 450 degrees. Okay, yeah, these are just rough temperature. No need to be exact. Okay, yeah, so you have the condition for this reaction. Okay, for contact process. And in the ionic state, we already saw what that equation is, what the reaction is. It's I minus and S2OA2 minus, the equation we just saw on the previous page, forming I2 and SO42 minus. Okay, so you may want to put down 2 and 2 here, and just write Fe3 plus on top. So the point I want to make is, transition metals, they can be catalysts in almost any state, either in the unbound state. You see, iron is not connected to anything. It's just iron. It's just elemental iron. So it is a catalyst here. It can still exert its catalytic property even when it binds to something else. Okay, like vanadium. You know, vanadium itself is a transition metal, but yet in this state, it's bound to oxygen, and it can still exhibit its catalytic property. Yeah, and you may think that stripping electron away from the transition metal would make the catalytic activity go away. But in this example, you see it does not. They can still exhibit catalytic property in ionic state. So therefore, don't just think that transition metal elements are catalysts. They compounds are catalysts. The ions are also catalysts. Okay? Is this point clear? So transition metal element, their compounds, their ions, they are all catalytic. They are all catalytic. Okay? So now write down a few important other important examples. Okay, right. For example, we have the first one here, the catalytic converter. Okay, I think there is a very high chance of you seeing this either in the MC or in the long question because this is a cross-topic concept, catalytic converter. First, it is related to, okay, or later if the Zoom chat expires, Janet, you can just join back the same chat. Okay, yeah, it says 10 minutes left for this Zoom lesson. Yeah, so I'll restart the Zoom. So for catalytic converter, it is used to remove two pollutants. Can you tell me what would these two pollutants be turned into? Well, if you make NO2, you're making it worse because NO2 is a brown gas, it can cause smog. Actually, we are turning it back to CO2 and N2. And can you identify the oxidation and the reduction reaction in here? Which substance is oxidized? CO is oxidized and NO is reduced. So it cannot be NO2 because if you say NO2, that means both are oxidation. You can't have two oxidation in a reaction. When one is oxidation, the other is reduction. Use this to check your answer. So you have reduction here. And short quiz. What is the origin of these two pollutants? So CO is a pollutant. Where does it come from?
Vehicles?
From
The exhaust pipes.
yeah, but what is the name of that process that forms CO? Incomplete combustion. Incomplete combustion. So write this down. CO is a product of incomplete combustion. Okay, so incomplete combustion. What about NO? Where does NO come from?
The what gases in the, what do you call it? The engine react with the
In the
air.
engine, yes. You know the car, the motor vehicle, it doesn't distinguish between nitrogen and oxygen in the air. It will just take both air. It will just take air in. And because nitrogen and oxygen are the two main components of air, under the high temperature, okay, and the car engine, they will combine to form NO. But let me ask you a question. Aren't these gases also present in the air? Why don't they combine outside the engine? Why can they only combine inside the engine? Explain.
High
Yes.
temperature?
Because of high temperature, and you forgot to mention something. Can you tell me what is the bond like in N2 and O2? What is the bond that holds two nitrogen and two oxygen together?
Covalent?
Yeah, covalent. What kind of covalent bond? Is it single, double, or triple?
Single? It's triple, actually.
Triple for N2
And double for O.
and double for O2. Which means, are these bonds strong or weak?
Strong.
Strong. I mean double bond and triple bond, right? Just think about it. They're strong bonds. So these strong bonds, they do not break outside the combustion engine because the temperature is not high enough to allow these bonds to break. So therefore, this should be a question that you think about when you learn this, okay, in the combustion. Now write this down. Question: why won't the N2 and O2 combine outside the combustion engine? Okay. So the answer comes in two parts. Okay, so part one is that N triple bond and O double bond are very strong. So what? They don't break under room temperature. Okay, so they are very strong. So therefore, only high temperature, okay, can break these bonds. You know, if you don't break bonds, you can't start a reaction. You can't start a reaction if you don't break bonds. Okay. So only high temperature can break these bonds and start a reaction. Okay? So very, very important concept. And catalytic converter, I would say it kills 3 birds with 1 stone, not just 2. Because it helps reduce carbon monoxide emission, it reduces NO emission. Why is NO bad? Can you tell me what problem do these pollutants that I put in the green box cause?
Toxic?
Yeah, CO is toxic, yes. Okay, so CO is toxic. It reduces the oxygen binding capacity. So you need to know this point. Reduces the oxygen binding capacity of blood. Because it binds to your hemoglobin 200 times more strongly than oxygen. So that's CO. And then we have nitrogen monoxide. How is this bad? This is not toxic, but it
Acid
can,
rain.
yeah, it can potentially cause acid rain. Okay, so NO, it can potentially form acid rain. So this is the process. NO will first react with oxygen to form NO2, nitrogen dioxide. And then the nitrogen dioxide will dissolve in water to form 2 acid. One you must know the name of, the other maybe not so much. Do you recognize these two acids? One of these you know. Yes, what is the name? Nitric acid. Yeah, HCl is hydrochloric acid, but when we name these acids, you don't call it hydrogen nitric acid, just nitric acid. This is nitrous acid. Okay, so these are what forms acid ring. Okay, so you can write down these two, they will form acid ring. So what about the third bird? Okay, I said it kills 3 birds with 1 stone, right? The third bird here is that it will change some unburned hydrocarbon, okay, back into what?
CO2.
CO2 and
Water.
water, yes. Okay, so write down the 3 pollutants. Everything I put in the green box, they are pollutants, okay? So the third pollutant, CXHY, the name of this pollutant, we call this unburned hydrocarbon. So unburned hydrocarbon. They can cause smog. You know when you look across Victoria Harbour, the yellow haze, okay, they are caused by unburned hydrocarbon. So it can cause photochemical smog. Photo means the formation of smog is caused by light. You all have heard of photosynthesis. Photosynthesis is possible thanks to light. Photochemical smog, they are also formed when light is present. So these 3 are pollutants. So these are the 3 birds you can kill with a catalytic converter. So A, B, and C. Pollutants. Okay, so you have pollutant A, pollutant B, pollutant C. So you reduce the emission of these 3 pollutants. Okay? Right. So that's the catalytic converter. What is the name of the catalyst used in catalytic converter? Platinum, yeah, or those noble metals like rhodium, okay? Yeah, just remember platinum. The platinum, they are coated on a honey. Yeah. Yeah, so photochemical smoke, cause photochemical smoke, which is why we need to get rid of them. This is also happening inside the catalytic converter. Both of these reactions happens inside the catalytic converter. So you install the catalytic converter, in the car, of course. Okay, so you put it in here. So this is where the engine is at. So this is where the car engine is at. Okay, so the engine. You install the catalytic converter behind the engine, so it will purify, okay, the exhaust gas, okay, because there will not be any CO, left, okay. Instead, you will have N2, so you can write down at the end what comes out from the engine, from the exhaust pipe: CO2, N2, and H2O. So these are your products: CO2, N2, and H2O. These will be your products. They are less harmful to the environment. Okay, less harmful for the environment. So this blue box, okay, it's not necessarily blue, I'm just making it a different color. So this is the catalytic converter. They may ask you why the platinum powder, they are coated on a honeycomb support. You know this platinum, you don't just buy a block of platinum and then stick it inside a car. You don't do that. You need to spread the platinum into fine powder, and then you coat it onto a honeycomb support. Why is that? What is the difference between a single lump of metal and a very finely divided powder of metal? Surface area, yes. Okay, so this is the question. Why is a finely divided platinum powder coated on a honeycomb support? So honeycomb support. This is to vastly increase the surface area. Both the finely divided powder and the honeycomb support ensures that. So honeycomb, when you look at these, okay, how they build their nest, they build honeycomb structure. This can present a very high surface area, a large surface area. You're just coating the platinum powder here. It's better than just buying a single lump of PT and just stick it inside a car. That won't work actually. This won't work. So maybe you can let Janet join again. Yeah, this is Zoom. I can't do anything about this. But every 40 seconds you will have to and the methane. So you see in here, this is a lump. This is not as good. Okay, so we have, right, so here we have, so this is the lump, and then we have these finely divided powder. Okay, so fine PT powder. Just write down one point. It vastly, okay, increase the surface area. And increasing surface area will improve the, is it the rate or the yield?
The rate.
The rate, okay, don't say yield, okay, you don't get more product. You get same amount of product in a shorter period of time, right? So by rate, I mean the rate of converting this pollutant into the harmless product. Is that clear? Okay? Yeah, so there are other, right, so there are, okay, so I think, right, yeah, so Jeanette, you should be back, okay, so, let me turn on the chat box, yeah. So we have the first reaction here. Can you put down some other reactions? Okay, so I'll just put down the equation here. You have manganese 4 oxide. What is the color of manganese 4 oxide?
Purple.
Permanganate will be purple. So
Very
manganese
pale pink.
is black. Okay, this is a black solid. Okay, so write down the name. And you should also be able to explain why is this called manganese 4 when you don't even see a number 4 in the formula. Why is this manganese 4 when you don't see the number 4 in the formula? Because the number 4 refers to the number of Mn. You know O is -2 each. So 2O will be -4. And Mn's oxidation number must therefore be +4. Okay, yeah, so this is not a typo. I know what I'm writing. It is manganese 4 when you see MnO2. Because that is the oxidation number of Mn. So X is +4. So therefore you have +4 in here. Okay, so manganese oxide. What does it do? It breaks down hydrogen peroxide into water and oxygen. Okay, in your body there is a similar reaction because your cell constantly produce hydrogen peroxide, which will damage the DNA and the protein. So your cell produces an enzyme called catalytic to do the same reaction. Okay, but we are here to study only the chemical aspect. So just know that this is a chemical catalyst. In biology, the catalysts, we call them enzymes. Okay, so similarly, yeah, if you're interested, you can write down catalyst. Okay, so this is the biological catalyst, aka enzyme. Yeah, and on top, this is the chemical catalyst, which we use in the lab. Yeah, the bottom thing. Yeah, you can do this experiment at home. Just go buy some minced pig liver. Pig liver contains a lot of catalyst. Just throw it in some hydrogen peroxide you get from the pharmacy and you will get an explosion. Well, a controllable explosion because there will be a lot of oxygen. Yeah, so catalase can be found in liver cubes. Liver, pig liver. Okay, so if you want to see this in action, just buy some pig liver, dice it, and then throw it in some hydrogen peroxide you get from the pharmacy. You will be able to see a spectacular, explosion. Okay, in your kitchen sink. Okay. So next up, we have also like the hydration. The polymerization of ethene. So remember when we polymerize ethene, we get what we call polyethene. And back in Form 5, you should have learned 2 different types of polyethene. What are the 2 types of polyethene? One is the HDPE, the other is the LDPE. What does HD stand for? High density. Oh, okay. You should have learned this in Form 5 and put down polyalkenes. Different types of plastics have some different variation. For example, PE, polyethylene, there are 2 subtypes. They are the HDPE. Okay, so HDPE, which stands for high density polyethylene. And then we have the low density polyethylene, LDPE. So the LDPE, they have polymer chains that are like in a mess. okay, like this. HDPE, they are more crystalline, okay, they are more tidy, you see. So they have like these fibers in here. Each of these fiber represents C, H, bracket N. So each of these threads you see in the structure represents a polyethylene chain. Depending on how you put the polyethylene chain together, you can just throw all the chains on the table in a mess. That's what we call LDPE. You know, low density means they don't pack as well. That's where the LD come from. HDPE means they pack very tightly. You can see they are like woven in a very regular arrangement. Which one do you think is tougher? Obviously, HDPE. Because then these particles, these polymers coming so close together means they can interact more tightly, interact more strongly, okay, with one another. And with these polymers spread out in space, yeah, the attraction will be weaker. So just put down stronger when the Wells force, and here weaker when the Wells force. This explains why they are used for different applications. Okay, so you know when you host a party, there will be party cups, the drinking cup, okay, the plastic, the disposable one. Low density polyethylene is for making that, or for making food wrap. Okay, you know these are very soft plastics. Okay, they crumble easily due to the weak Van der Waals force. The HDPE, however, it can be used to make plastic chairs like these ones from IKEA. Okay, yeah, plastic chairs. Okay, they're tougher. You don't want to sit on the drinking cup. The cup will collapse under your weight. But the plastic chair will not, because it's made of a tougher, a hardier form of polyethylene known as HDPE. So plastic chair. It's not only polyethylene that we have slight variations. Okay, we have also PVC. Do you remember what PVC is?
Yes.
What is the name?
Polyvinyl chloride.
Polyvinyl chloride, close enough. Okay, so polyvinyl chloride.
Chloride.
Yeah, so polyvinyl chloride is related to vinyl disc. If you know what vinyl disc is, you have exposed your age. Okay, so vinyl disc, so you're now pretending you don't know what that is. Or you really don't know what that is. It's the disc that you put on like the, I don't know what you call it, is it a xylophone or something like that?
I actually don't.
It's in the 90s, it looks like
Okay,
that.
yeah, that's why I said you're exposing your age if you know what this is. This disc is known as the vinyl disc. It is, yeah, this is vinyl disc, okay? This is the relation. So PVC, yeah, PVC. Okay, so we have PE here, PVC. PVC, there are also two subtypes. Okay, one is called the plasticized. So plasticized PVC. And the other is unplasticized. So to plasticize something means to make it softer. So plasticized PVC is therefore softer. Okay, they are soft enough to be used as garden hose. Okay, the garden hose. So let's say this is the gardener. So he's doing the rubber hose. Yeah, so the water come out of it. Okay, so this is the garden hose. It has to be soft, so we can bend around corners. Okay, unplasticized PVC, they are tougher. They are harder. So this is softer, and this is harder. So them being harder means they can be used to carry water in pipes. Okay? Yeah, so this is water pipe. And you need to know the chemistry, okay, of how adding plasticizer changes the toughness of the plastic. So here, let me show you the chains again. Each of these chains represents polyvinyl chloride. Polyvinyl chloride means polychloroethene. Okay, so this is polyvinyl chloride. You may want to write down the name here. Polyvinyl chloride, aka polychloroethene. Meaning they are made from chloroethene monomer. Do you recognize this? This is made from chloroethene. So you have ClHHH. When you polymerize this, you will get polychloroethene. So this is chloroethene. This is polychloroethene. Okay, so polychloroethene means polyvinyl chloride. So how is the packing of chains different in these two forms of plastics? Okay, for plasticized PVC, so we add plasticizer. So plasticizer are like some spacer molecule which you insert between the chains like this. Okay, so they are like there to keep the chains apart. Okay, so that the chains don't come as close together. These orange block are what we call plasticizer. So I think rumor has it that plasticizer is also found in the those gelatinous thing in the bubble tea. Bubble tea. Do you drink bubble tea? No, none of you drink bubble tea.
No.
You drink bubble tea. So because there may be plasticizer in bubble tea, and for the ladies, plasticizers may disrupt your hormonal balance. Okay, that's
That
not great.
exists.
Okay, well you don't die from it. You don't die from it, but you get a very out of sync menstrual cycle. Okay, like something like that. Okay, so this is
Drink has
plasticizer.
bubble tea.
It disrupts your hormonal balance. Okay, so they disrupt
I'm not drinking bubble tea.
hormonal balance.
Yeah.
Not only do they disrupt the chains, you see they insert themselves between the chains. Yeah, they also disrupt your hormonal balance. Yeah, and for unplasticized PVC, if you do not add the PVC, if you do not add the plasticizer, the chains would they be closer or further apart? They will be closer together, right? That means they are stronger. This is why it's harder. Okay, so you can put down in here, use these dots to represent the forces in between those chains. You see here, you have weaker van der Waals. When you insert the plasticizer in between the chains, you see you keep the chains apart. But if you do not add any plasticizer, this is what we call unplasticized PVC. You see the orange thing are now gone. The attraction will be stronger. So therefore, to your surprise, water pipes and water hose, they are made from the same material. It's just that one has plasticizer, one does not. That's it. Okay. So that's PVC. And for PS, what does PS stand for? Not playstation, but polystyrene. Okay. You should have heard of something called styrofoam. Okay. Styrofoam is one type of polystyrene. Okay. Called it expanded polystyrene. So this is PS. PS, there are also two types. The unexpanded and the expanded. Expanded polystyrene is what we call styrofoam. Okay. There is the word foam in it because we are blowing a gas inside to reduce the density. So this is why styrofoam sheets they float on water. Okay. So you may not know that unplasticized PVC it is clear, a plastic. You can find it on CD disc. You may not have CD disc anymore at home, but so nobody listens to CD disc anyway. Okay, so we use MP3 right these days, or just listen to music on the phone. So the disc, okay, is made from this clear plastic called unexpanded PS, polystyrene. This is unexpanded polystyrene means styrofoam, STYROFOAM. Okay, so styrofoam is not a clear plastic. Okay, it is opaque, white plastic. So opaque white plastic. It is known for its very low density, so it floats on water, and also known for its insulating property. Okay, this is why we use it to keep hot coffee. Okay, so right. So this is the styrofoam. So these three types of plastic, you need to know that there are two subtypes of each. For PE, the two subtypes are HDPE and LDPE. For PVC, the two subtypes are plasticized PVC and unplasticized PVC. For PS, the two subtypes are unexpanded PS and expanded PS. So is this clear about the three types of plastic and their subvariants? This is part of DSE. You can't just know PE. You need to know that under PE there are two types. One that is stronger, one that is weaker. Okay. So let me put down harder and softer. Is that clear? Okay, so now back to here. What was it that I was talking about? The second catalyst. Okay, so this is not. So here you can put down AlC2H5 So we call this tri-ethyl aluminum. Okay, so it looks like this. Okay, so you have Al, and then you have C2H5, C2H5, and titanium chloride. So titanium chloride. So this is known as the cyanonator catalyst. So it is for making HDPE. Okay, so write down high density polyethylene. So you know there are two types of polyethylene. So how do we make each type of polyethylene? Well, it's different. We need different conditions in order to make these different types of polyethylene. So we will need to use 100 degree and 50 atm. Remember conditions, right? These are conditions. Condition means you need to say what the catalysts are, what the temperature is, what the pressure is. So this is the condition for making HDPE from ethene. Okay, so you'll need N of the ethene in order to make this polyethylene on the right. Okay, so you have bracket N. Okay, so you can then make HDPE using this catalyst. Collectively, AlC2H5 and TiCl4 is the cyanonator catalyst.
Oh, can
okay.
we-
Yeah, so you
Should
can
I
just.
remember that?
Well, I think either way is difficult. Okay, but maybe you want
The
to
name,
remember the
the
formula.
name.
Yeah, the name is even more difficult. And remembering the name doesn't have you remember the formula. If I were you, I would just remember the formula.
Okay,
instead.
don't care about the name.
Yeah, so these two, okay, collectively, okay, they are called the cyanonator catalyst. Okay, so and that should wrap up the this chapter.
What is the name for the above one? The above.
Oh,
The name
what do
for-
you mean the other one?
No, the up one. The
The top
MaO.
one.
Yeah. What is the name of that reaction?
This is manganese forms.
There's no name for the reaction.
And the biological version of these catalysts will
But
be called
because the
catalysts.
first one use the catalytic converter, right?
Oh, yeah. The first reaction is the catalytic converter.
What about the second one?
Or the second reaction will be here, the decomposition of hydrogen peroxide.
Okay.
So the decomposition of H2O2. So this reaction is involved in the making of elephant's toothpaste. Have you seen elephant's toothpaste before? Yeah, okay. It's actually mixing hydrogen peroxide with detergent, with some dyes. Yeah, you can do it at home if you want to clean up at the weekends. Okay, yeah, you can just mix hydrogen peroxide, put some detergent in. You add detergent in because you want it to foam up even more, and it will form the elephant toothpaste. If you don't know what elephant toothpaste is, you can search it up on YouTube. Yeah, it will form something that looks like toothpaste out of your reaction flask. Okay. The third reaction here that is also of particular importance is the polymerization of ethene, yes, okay, of C2H4 into HDPE. Okay? Right. So that should wrap up the chapter. So in this chapter you know a few things. Okay. Oh, and also I forgot the color. Okay, the color is mostly just spectral recall. You either remember it or you don't. Okay, so I'll just put it on the next page. Some very commonly asked transition metal ions and their colors. Okay, so here, write down transition metal ions and compounds, as well as their colors. So you know the different gemstones. Okay, if you have read a book about gemstone before, you know different gemstones, they are differently colored because of the presence of different types of ion. Okay, so for example, you have nickel 2+, which is green. Yeah, you can have copper 2+, which is blue. Okay, I'm not talking about the color in the flame test. I'm talking about the color of the ion in solution. So this is the ion in solution. But strangely, the oxide of copper, what color is the oxide of copper?
Reddish brown. Black.
When you say reddish brown or black, okay, you're right, okay, but you're referring to different types of So if you have Cu2O, or especially for students doing biology, you know Benedict's test. The red precipitate, Benedict's test. Yeah, the red oxide is copper 1 oxide. So this is copper 1 oxide. Why is there copper 1 when you don't see a number 1 in here? Because the oxidation number of Cu is plus 1. And this is copper 2 oxide. And they can't have any more different color. So this is black. Copper oxide is black. Okay? And copper 1 oxide is red. Yeah, this is what Benedict's test is doing. You know Benedict's test is also a redox reaction. Because glucose is an aldehyde. What can aldehyde be oxidized to? What can aldehyde be oxidized to?
Carboxylic acid.
Carboxylic acid. So you have an oxidation reaction. At the same time, the ion in Benedict's solution is copper 2 plus. It is reduced to copper 1 oxide. So Benedict's test is a redox reaction. Yeah, so what else? We have also Mn. So when you talk about Mn2 plus, it's colorless or mostly pink, okay, or very pale pink, so pale that you may have mistaken it's colorful, colorless. And then we have MnO2, which is a black solid, okay, so it is a black solid. And then we have MnO4 minus, which is a purple ion, okay, so this is a purple ion. Yeah, and then we have Cl3 plus. Yeah, I know at this point they may all just look like random facts, okay, but still you need to know. Cl3 plus is green. What is the formula of that oxidizing agent that also has chromium in it?
Cl2O7 minus.
Cl2O7 2 minus. Okay, so Cl2O7 2 minus. And then there's the brother of Cl2O7 2 minus, which is ClO4 2 minus. What is the color of ClO4 2 minus from Form 4?
What are you talking
You learn it in Form 4 in the second chapter. It's yellow.
Oh, right.
This is yellow.
There's 3 chapters.
So know the name of these ions. Okay. I know they look like random facts, but you have to remember that. Okay. So this is dichromate ion. And this guy below, we call it chromate ion. Because one has 2 Cl in it, therefore di means 2. One has only 1 Cl in it, so you don't see the word di in here. Yeah. So can you tell me which of these reactions is a redox reaction? So Cl2O7 2 minus becoming Cl3 plus, and Cl2O7 2 minus becoming ClO4 2 minus. Which of this is a redox reaction?
First one.
The first one. Is the second redox?
No.
No. Okay. That's because the oxidation number did not change. You can see that chromium's oxidation number went from what to what in the first reaction?
From plus 3.
Plus 6 to plus 3. Yeah, so this you can say is a reduction. Okay. What about the second one?
Plus 6 to plus 6.
Yes. So therefore don't think that when you can write an equation it must be a redox. No. Writing an equation doesn't mean you get a redox reaction. So can you write down, so this is one thing, plus 7H2O, 14H plus 6E minus. And for the second equation, you have 2 ClO4 2 minus plus H2O plus 2H plus. So this is actually an equilibrium reaction. Okay? Right, yeah. Okay. And I need to tell you all something. I'm leaving next one.
Wow!
Puta, di naman bago.
15. Because I don't know how to
Wow.
all one and all 3 students. It's really well, I don't know how to put it. It's really a challenge to me for Form 1 and Form 3. It's like when I walk in a classroom, it's like I'm in a market.
Very true.
It's like I'm walking to a wall.
This is the fifth teacher with
He's gonna be a
So
fun teacher.
But then, yeah, I will be conducting the makeup lesson, yes. And also next week, we will do the full
Can you be
on
my 550?
2.5 hours next Tuesday.
Yeah.
Yeah.
Yeah, so therefore you might want to use the math room at the end of the lunch, and then we will have a long marathon of 2.5 hours, like exam. Of course, you can go to the math room like in the real exam, but just know that
Yeah.
it will be a mock that predicts your grade. Okay.
Sir, can you teach us after you leave, please?
Okay. Anyone?
Can you teach us after you leave?
Because I will be at another school. I will be at another school. Yeah. So but yeah, you can ask me questions. Okay. Yeah. But yeah, I think it's better you ask me questions like during this time. Okay. During this time. Yeah. But
You got it's only been 2 months.
Oh my God.
2 months.
it's really a challenge to me. Yeah. I hope you all understand. They all 1 and all 3, they are. I don't know how to put it. It's like a disaster. I almost cried.
Sure, don't give exam about 1 month.
Why is the junior form like this?
I cannot let the other students come. Okay, yeah, but
Just play the principal.
I will continue to do my best to help you get through these topics. So let's make sure we finish at least up to the middle part of the